In this lesson, I'm going to introduce you to the concept of vectors. Now, just as a bit of an introduction here, it says, is it possible to swim straight across a river? The answer to that question is yes, only if there is no current, because the truth of the matter is that most rivers do have a current, and so it would be virtually impossible for you to swim straight across that river. So as a result, you really swim the displacement, which means that you swim a certain distance across the river in a direction, though, that is affected by the current. So we could draw a couple of simple pictures here to show you what I mean. So if this is our river, if there was absolutely no current at all, then you could swim straight across that river and your direction would be perpendicular to the riverbank. But in reality, there's always some kind of current in the river. So therefore, even if you are aiming to swim straight across the river, what's happening is there is also a current in that river. And so the current is going to push you as you're swimming. So in the end, you end up over here instead of where you meant to be, which was directly across the river. So that kind of gives you an idea when we talk about vectors. Vectors have magnitude and direction. So before we get further into this idea of vectors, we're going to talk for a minute about the difference between a scalar and a vector. So a scalar is a quantity or measurement that has only magnitude and can be expressed using a single numerical value. So time, temperature, volume, age, height, and so on. Those are all examples of scalars. Compared to that, a vector has both direction and magnitude. So in the example we were giving at the beginning, your displacement vector, the green one I've indicated above, has direction and it also has magnitude. So the distance you're swimming would be the magnitude, and the direction you're swimming, which is affected by the current, would also be part of that vector. So a vector has both direction and magnitude. Now, often we represent vectors with a little, in terms of the notation, we use a little arrow above the letter, as you can see in this case here. So they can be represented various ways, as you'll see here in the diagram. So usually we represent vectors as directed line segments, so there will be an arrow on one end of your vector. And the end with the arrowhead is called the head of the vector, and the other end is the tail. So the tail is what shows you where the vector originates, and the head, it defines the tip with an arrowhead. Sometimes a vector can be represented using two letters. So we have that here with vector AB. So again, the first letter in the notation indicates where the tail of the vector is, and the other letter indicates where the head of the vector is. Now we have some terminology to go through here when dealing with vectors. So equivalent vectors or equal vectors have the same magnitude, so the same length, and the same direction, but they may have different positions. So for example, U and V here are equivalent vectors, and AB and CD are equivalent vectors. So we could say that vector U is equal to vector V, and we could say that vector AB is equal to vector CD. Opposite vectors have the same magnitude, but they're opposite in direction. So looking here at vectors A and B, you can see that they have the same length, these directed line segments, but the head is on the opposite end, so they are opposite in direction. So then we could say that A is equal to negative B, and B is equal to negative A. The direction of a vector can be expressed in two ways. Either as a true bearing, which is sometimes just called a bearing or compass form, which is an angle measured clockwise directly from north and expressed as a 3-digit number. So in your example here, that would be this angle here of 150 degrees. So the same vector, though, could also be expressed using what we call quadrant bearing, which is an angle between 0 and 90, and it's always measured either east or west of the north-south line. So in other words, from the north-south line, if we measure 30 degrees east, then we fall onto the same vector. So we can either represent it as 150 degrees, which we know is 150 degrees from true north, or south 30 degrees east, meaning from south you move 30 degrees towards east. Let's do a couple of examples to make sure we've got that. So it says express as a true bearing, north 50 degrees east. So north 50 degrees east would be in quadrant 1. So from north, we're going to go east 50 degrees. So in other words, to express that as a true bearing, it would just be 50 degrees because a true bearing is always measured from due north. South 10 degrees west means from south, we go west 10 degrees. Now to express that as a true bearing, we need to start from north and think of what angle it would take to get to south 10 degrees west. And that angle would be 190 degrees. So basically it would take 180 degrees to get to due south, and then another 10 degrees would take you to 190 degrees. Let's see if we can make that a little bit clearer. Okay, so true bearing and quadrant bearing, both we need to be familiar with for our vector application questions. All right, as our last example in this lesson, it says you are crossing a 12-meter river in a rowboat. When you reach the other side, you discover that the current caused you to reach a point which is 5 meters away from where you should have landed. Calculate the magnitude of the displacement vector. So if we are trying to swim across this river, which has a width of 12 meters, but we have a current that caused us to land 5 meters away from that, the question is asking us to find the magnitude of the displacement vector, which would be the one you're actually swimming along. So let's call that vector x. Now, for this question, we can use the Pythagorean theorem to find the length of the displacement vector. That's also called the resultant vector. So the Pythagorean theorem, as well as trigonometry, are going to be very useful in solving your vector questions. So using the Pythagorean theorem, we know that the magnitude of x squared is equal to 5 squared plus 12 squared, which is 25 plus 144. So the magnitude squared is 169, which means the magnitude will be the square root of that. So the magnitude is 13. So therefore, the magnitude of the displacement vector is 13 meters. And that concludes this lesson.